Okay, let's get started again. First need to reset this thing. Before the break we talked a lot about the receiving, the multipath, the interferers, and the parameters that you can use to qualify that. So for the wireless system as a whole, we came up with these parameters. Now let's look at the parameters not of the system as a whole, but of the individual transmitter and the receiver that we need to specify to achieve the required range, spectrum use, and so on. If you look at the transmitter, then there are parameters like transmit power, the frequency range, the bandwidth, modulation accuracy, spurious emissions that you have, the duty cycle of the transmitter, whether you can have it on all the time or not, the efficiency, so how much power you transmit versus how much energy you consume per second from the battery or from the energy source, the directivity, so how much you focus your signal, and many, many more parameters. And equally, for the receiver, you also have a whole list, like the sensitivity, how weak a signal can you detect, the robustness against interferers, the amount of emissions that your receiver has, because even though you intend to design a receiver, in reality it might also transmit some signals unintentionally, but it still happens. And again, you need to meet specifications for that. Power dissipation, because even the receiver takes power. Frequency range that you need to cover, the bandwidth, the modulation, and also there many, many more parameters. And of course, it's nice to have all these parameters. But if you want to deal with them in any practical way, in a scientific way, we should not just know that sensitivity is important and the interferer robustness is important. We need to know how to specify it in a way that is very clear, that there can be no misunderstanding. Because otherwise you get a discussion, and this is not literally what I encountered, but in industry I had many discussions when I was a development manager with people in marketing, and people in marketing would say something like, this receiver has to be very sensitive. Okay, so I would ask, well, how sensitive does it have to be? No. Very, very sensitive. Okay. Then can you be more precise? As sensitive as possible was very frequently the answer. Now, this is the reason why we need a better way to specify. This is not a good basis to invest for a typical radio development, 15 million euros in time and masks and silicon to find out whether what we think is as sensitive as possible was the same as the guy from marketing was thinking. Right? So we need preferably a parameter that is quantified, that is a number. So let's think about it. Can we find a number that tells us the sensitivity of a radio? So if we look at this radio and this radio, right, we know that this is a lousy radio, this is a good radio. Can we think of a way to put a number on that? So what I'm going to ask you is in groups of, let's say, 2 people. Let's try groups of 2 people initially. And let's take 5 minutes for this so that you can think about, really think about, how would I put sensitivity in a number? And take some time. I walk around, so you can ask me questions. You can discuss with me what you propose. And then in 5 minutes we will get together and we will see whether we've come to a consensus or whether we have more opportunities for discussions. So let me start 5-minute timer. And by the way, some of you might think it's so simple that you can do it in 10 seconds. It should be okay.
is equal to gain of the antenna. I think that's the Can there be a limit to this? Yeah, my mind is not correctly. Coming directly to us. Everything increases. We can explain more by saying that first equation of equation and then it can't increase drastically. If it increases drastically, then all these terms also will increase drastically and the entire communication will be
Sensitive. This time I didn't make it around all the way. There were too many interesting discussions on this side. I promise next time I will start on the other side. Then, of course, you have to stay in the same side next lecture. I've heard a lot of interesting discussions. And what I heard was that initially it seems it's not so difficult. Right? If you want to say sensitivity, you can say something like, that's easy. I need to be able to receive a signal at the antenna input of any signal that's at least, let's say, minus 90 dBms, which is an amount of signal power, and we'll come back to that later, how that's defined. Everything at least minus 90 dBms I can receive, and so I call that a sensitivity of minus 90 dBms. And from minus 91 dBms on, I don't receive it, so that tells me that that's my sensitivity. But when you think about it, it's not so easy, right? Because how do I define the point where I stop receiving a signal? When we were passing down this radio from line to line, the reception didn't abruptly stop. I mean, this radio, yes, that's a cheap one. But this one, you could hear the signal getting weaker and weaker, and the noise stays the same, so it was more and more difficult to hear the station, but it didn't abruptly stop. So at which point do you define that you have reached your sensitivity? It could be that somebody with better ears could hear a very weak signal than I can, because my ears are old and I've listened to far too loud music over the years, so I probably will already stop hearing a station much earlier than many of you. But that doesn't help. For defining sensitivity, we need to know how to define that a signal is still being received or not. And one way of doing that is that in addition to the sensitivity at the input, the received power, you say, I have a certain quality of the received signal. And that can be, for example, the signal-to-noise ratio. I require that my station, when I listen to it, is 10 dBs better than the noise coming from the loudspeaker. Or, for digital systems, I can translate this into a certain bit error rate. Right? I can say that I want at least 990 out of 1,000 bits to be correct. And the input level, the antenna level, where I reach that signal to noise or that bit error level, that I call sensitivity. And for digital, we can try that as well. I brought a speaker. I hope that one is working. And we can also play some music over that one, theoretically. And so if we hand this down, again with apologies for the music, if you can hand it down the line. So there's already, we can see with digital connection, the connection is a lot better, right? We do not hear any deterioration of the signal. we cannot go far enough away. So what I will do, I will walk through the building a little bit, make the distance a little bit larger until the signal breaks. I'll be back in a minute.
Sound is gone. It's lost here already.
Hi. Ik ben het college aan het geven. Oké. Ja, ik kom er een andere keer terug. Ja. Okay, what did you hear? Did you actually hear the signal getting worse and worse and the noise coming up? No. Instead, what happened probably, I guess, I wasn't here, but I can always listen to the recordings later, but I guess the music stopped fairly abruptly. Right? Or didn't it? No, it did, yeah. Okay. So what happens is that in digital, you can correct mistakes, right? There's error correcting codes. And that means that up to that bit error level that the error correcting code can handle, the music sounds perfect. And after that, it stops abruptly because the error decoder, the error corrector says, I can't handle this anymore. Just give up and switch off the music. So in many digital systems, rather than a signal-to-noise ratio, you deal with a bit error rate. That is also directly related to the signal-to-noise ratio if you know the modulation. Because for any kind of modulation, you can find in literature what's called the waterfall curve that relates signal-to-noise ratio to the bit error rate. And these curves look all like this, and with some variations. So they might also look like this or like this, but very, very similar. And this might be for, let's say, FSK, frequency shift keying, and this might be for QAM. But these curves you can find. And so in the same way that for analog systems, you have a signal-to-noise ratio that you define, through this curve, you can relate that signal-to-noise ratio directly to the bit error rate that you want to have, let's say, bit error rate of 10 minus 3. So every 999 bits that are correct, you allow one wrong bit. And then you can find the corresponding signal-to-noise ratio if you know the modulation. And then, and that's one of the nice things about digital systems, the error correction allows you to have perfect reception until that point, and then it stops abruptly. That's also the reason why I didn't start using that in the first demonstration, because to understand what's happening with noise and with interference, it's much nicer to have an analog system like this radio, because you can actually hear the interference, you can actually hear the noise, and you can hear your signal. Whereas in a digital system, the only thing that you hear is, now there's sound, and it's perfect, and now there's nothing. And you don't know whether it's because of interference, or of noise, or of multipath, or anything. Nevertheless, personally I prefer digital quite a lot, because most of the time you have perfect reception. So, next question is, and we also discussed that on this side, now that we know how to define sensitivity as the smallest signal at the antenna that gives me a certain signal-to-noise ratio, a certain bit error rate. If I know the definition, how do I know that that's what the limit is, when I can't improve any further? And why would I want to know that in the first place? Well, the reason I want to know that is basically because this guy, right? If he tells me that I make something as sensitive as possible, and I design a Bluetooth receiver, and the Bluetooth receiver has a sensitivity of minus 98 dBm, and I said, that's as good as it gets. I've worked with a team of very experienced people for 3 years, and this is what we got, and can't be any better. The question remains, if somebody from a competing organization, let's say Delft University or Twente University, with a team of 50 people, maybe almost as smart as we are, but with 10 times as many people, and they work for 10 years rather than 3 years, maybe they can do minus 110. And I don't know. And this marketing guy, if he ever finds out that there's another organization that's doing better than we are, I'm in deep trouble, right? So I have an interest as a designer and as a scientist to know where the limits are, because then I can say, this is what I achieve, this is what you can theoretically achieve, that's only 3% difference. If you wait another 10 years, I can make that 2% difference. What do you want? So that's the reason for having this interest. Now the question is, how do we find this limit? How do we know that a limit of minus 90 dBms for a bit error rate, for a signal to noise ratio of 10 dBs, whether that really is as good as it gets? How would you do that? Well, actually, there was a very good suggestion that I heard, and a very practical one. You design a radio, or you make a model of a radio with ideal components. And if you assume that all components are ideal, they don't add any noise, they have perfect gain, they have perfect properties, then that is as good as it gets. That gives me my limit. And indeed, when you think about it, that model can be quite simple. I have my antenna signal, I go through this radio, and this radio I can model in two parts. There's a perfect part, there's a perfect radio inside this box, and to the output signal of this perfect radio, I add some noise. It's like with students. Inside every student there's a perfect student, and once in a while they add a mistake. Right? That happens. Now, with radios it's like this. You can model it as a perfect radio, and you add some noise to it. Then the perfect radio, the best sensitivity I can achieve is if I add 0 noise to it, and I can use that as a benchmark. Now if I add 0 noise to it, the best I can do at the output of this radio for simple modulations like QAM and any linear modulation basically, for any linear modulation we know that superposition holds. So we have a signal to noise ratio at the input and a signal to noise ratio at the output. And if everything is perfect and linear, then the best I can do is that my output signal to noise ratio is equal to my input signal to noise ratio. That's it. I cannot do better. It's like this tomato ketchup stain, right? You never get rid of it. Once you have noise, the noise is not going to go away. Yes, I can amplify my signal, but I will also amplify the noise. And so the signal to noise ratio stays the same. So another way of quantifying now the quality of this radio is I can say, well, I have a quality number that is my signal to noise ratio at the input divided by the signal to noise ratio at the output. And this is what we call the noise factor. And this is a quality indicator for my radio. A perfect radio, the noise factor is 1. And for a radio that is worse, where I have a larger, sorry, I'm doing this wrong, right? It's the other way around. No, sorry, the signal to noise ratio gets smaller. Yeah, it's like this. So if the signal to noise ratio at the output gets smaller, then the noise factor goes up, and it tells me that my radio is not perfect. And now I can define my sensitivity as from this, because I know at the input I have a signal to noise ratio of my signal power that I receive, the sensitivity, divided by the noise. What's the noise at the input? Sorry? Low noise? No noise? Ah, that would be nice. Are you sure?
Only thermal noise.
Yes, thermal noise. Yeah.
Short noise.
Short noise is not inevitable. Thermal noise is inevitable, but short noise is something that you add yourself by doing not ideal design. No, sorry. Yeah, okay. No, sorry, there's two kinds of short noise. You mean flicker noise, 1 over F noise.
But then it's for the RF systems, it will not matter.
Yeah, for RF systems, so the frequencies we are talking about, you only have thermal noise basically. And thermal noise comes from the fortunate fact that the temperature here is non-zero. Right? Even though when you walk outside sometimes you can doubt that. But in fact it's still non-zero, non-zero Kelvin. It's definitely much higher. And this high temperature causes noise. Basically because all atoms, all ions are moving, they are shaking, and the electrons get influenced by that, and you get small variations in currents and voltages. And that means that we have a noise power at the input. And the nice thing is that noise power at the input for any radio that only has thermal noise, so any perfect antenna gives you a noise power 4kT times the bandwidth. That's all the noise you get. And you can see here if the temperature would be zero, I would get rid of that noise, but that's not the case. You have to keep in mind that this is the temperature of the object that the antenna is looking towards. Right? So if I have an antenna that has a very narrow beam and I'm looking at the transmitter and that camera over there, then it will be a temperature of about 290 Kelvin, so 20 degrees or so. And in most cases I can work with that number. The case where you need to watch out is if you're in radio astronomy and you're looking towards the stars. It's a lot colder up there, and then you need to work with a lower temperature. But in general, most designs that we will do, the T will be ambient temperature, and then you have 4 times the constant of Boltzmann times the absolute temperature times the bandwidth. That's the noise you get. So we know the noise. This is our sensitivity. We also know the noise that we have at the output, right? So we can put this in here. We know that the input signal to noise is our PR, the received power, divided by the noise, 4kT times the bandwidth, divided by the signal to noise at the output. So if we know that we need a sensitivity of minus 90 dBms at the output for a signal to noise ratio of 10 dBs, then we can put that here in the formula, and that gives us the noise factor. If the noise factor is 1, then this guy from marketing is asking the limit, right? Really the very best possible. If the number is larger than 1, I know I still have some margin. If the number is smaller than 1, it's impossible. It's as simple as that. Or in other words, the best sensitivity that you can get, received power, equals, and now I have to do it right, F times SNR at the output, divided times 4kT times the bandwidth. That's the best sensitivity, and then the noise factor makes up for the real sensitivity. So this basically gives you the limit of what you can do in transceiver design. And later, when we go into circuits, you will see why this F, sorry, it should be there once only, why this F is always significantly higher than 1. Next question then. Okay, we have now a good handle on sensitivity. We know how to specify it. We know what the limit is. Let's think about interferers. Can we handle that in the same way? And so the first question is, do we, in a similar way as for sensitivity, can we define what the strongest interferer can be? For example, can we say, worst case, our interferer is equally strong as the signal that we want to listen to? Is that true? Or could an interferer be stronger than the signal we want to listen to?
If you have this radio right next to the radio station, then probably the interferer is much stronger.
Yeah, I agree. That's exactly the problem. So the situation where this is me, right? You can tell from the glasses and the beard. And I have this lousy radio. And I'm next to a big transmitter. And very, very far away, on this side, there's TUE. And there's U with this nice, very small transmitter. And this distance might be, let's say this is in Hulsberg, right? So this would be 70 kilometers. Let's say this distance is, well, I don't want to be closer than 10 meters. This thing is transmitting 0.1 milliwatts. This one is transmitting 10 kilowatts. This guy is going to win, right? So my interferer can be a lot stronger than my wanted signal, and a lot. I'm not talking just 10 times or so. I'm talking thousands, hundred thousands, millions of times, if you're unlucky. And the factors in there are the transmit power, can be different, but especially the distance. And so an important thing is, can we limit the distance? Well, we already know, when you think about it, if we know the sensitivity, and we know Freeze equation, right, then we know the maximum range of our system. Okay? So this distance, if it gets larger than the maximum range of the system, I don't care about interference, because no way I will pick up the wanted station anyway. So this distance, maximum distance where I care, is the maximum range of the system. So the interesting question is there a minimum distance to interferers? Can I guarantee that you will never get closer than a distance of x, whatever x is, to an interferer? Because if I can say that, then I can start talking about the upper limit for interferers. If I cannot say that, wow, then we have really a job to do, right? Because that means there's no upper limit for interferers. And suddenly our lives get a lot more interesting. So what is it? Do we have a minimum distance to our interferer? I mean, but even the wavelength of this thing is about 3 meters. And I can bring it much closer than 3 meters. I can even take the plastic off and make the antennas touch. It seems like in practice, there's really no limit. I can make these things as close as I can. And that's one of the drama of radio. I mean, there is really no minimum distance in practice. And yes, what you can do, of course, is you can make a user manual for a transmitter or a user manual for a phone and say, don't put it closer than 10 centimeters to any transmitter. Who of you ever reads a user manual? Anybody? Okay, there's a few. Very good. And you will find many of these warnings. Right? Don't do this, don't do this, don't put it close. But the problem is that 97% of people don't read the user manual. And those 3% of people that do read the user manual, and we already are above average, they don't really remember and they don't really understand, and they still do it. There is no limit, really no limit, to what customers and consumers will do with equipment. And so, in one sense, that can make you desperate, right? Because you might say, oh, but then there's no solution. There's no way I'm ever going to make a radio that's robust against all possible interference scenarios. And that's true, there's just no way. But the good thing is, you don't have to. Because people are used to radios. You can always break a radio. You can always find a situation where a radio is not working. Very famous case. People have these nice desks with metal drawers underneath. People put their cell phone in a metal drawer. It's not good for your received signal strength, because it's like a Faraday cage. They put it on top of their laptop. It's not good for interference. But also people know that in some cases the reception is bad, and they just accept it, and they move a little bit away, or they put the phone somewhere else, and suddenly it works again. They might not understand exactly why, but it's because of this. So We don't have to make radios that always work, because that's impossible. But we need to define, and that's somewhat arbitrary, we need to define a limit where we say we make a system that works up till this distance, and it has to be a practical distance. In-house, you probably cannot ask people to stay away at least 50 meters from any transmitter, because most houses are not big enough. But maybe 10 centimeters is a reasonable number. And then you can argue with people in marketing whether it should be 5 centimeters or 15 centimeters or half a meter, but you can find some reasonable distance, and that's not a hard limit like we discussed with sensitivity, which has to do with thermodynamics and Boltzmann constants and so on. That's really very hard. You cannot do better than that. Law of physics, you go beyond that, you get burned. This is really interpretation. This is a choice, an arbitrary choice for a certain system, where you say, I want to make a system that works in most cases, but there will always be a few people, and believe me, there will always be a few people that manage to break it. There's nothing that you can do against that. So there's, in that sense, a very important difference between sensitivity and noise on one hand, and interference and distortion on the other hand. Next time, I'm going to go in, whoops, there was a lot more I wanted to discuss this time. Yeah, next time I'm going to go into transceiver specifications, because thus far we've discussed system specifications. Now we're going to talk about transceiver specifications and cascading functions and architectures. So what I would like to ask you is to look through the slides that I will put on Oase, so that you already have a lot of the knowledge about these things. Next time we will start with a short test where I can see to what level you already understand these things, and then we'll take it from there. I will also start putting this information in this blended learning environment that I mentioned, that you can find on this website. But since the student assistants has not started yet, or the student assistants, because we might have two, that's going to be somewhat slow this week, and it will pick up hopefully next week. Are there any last questions? If not, then thank you very much, and see you on Monday.